Good morning dear students, welcome back. So this is my next video on quantum computation. This is exclusively for computer science and allied branches for engineering physics VTU syllabus. So in my previous videos so far I have explained up to unitary matrix, identity operator, and then Bragg vector, Ket vector, importance of Bragg vector. So these things we have discussed so far. Now let us proceed further. Just I revise unitary matrix. What is unitary? When do we call a matrix as unitary? Suppose if U is a matrix, right, a member of a particular vector space, U dagger you take, you know how to find U dagger. U dagger is nothing but Hermitian. So U into U dagger, if it is equal to I, identity matrix, then U is called unitary matrix. Okay, so U dagger, that is Hermitian. Hermitian is nothing but complex conjugate and then its transpose. I already explained what is complex conjugate, how to find the transpose. So let us not repeat it again and again. You know by now already how to find the Hermitian. Now let us try one or two examples for this. Let me try first example. Let us check whether this matrix is unitary or not. So I consider matrix 1 by root 2 into, let me take 1 plus I minus I. 1 plus I minus I. Let us check whether this is a unitary matrix or not. How to check unitary matrix? First we have to find the Hermitian of this one. How to find the Hermitian? First we have to find the complex conjugate. What is complex conjugate? Retain the constant terms as it is. Wherever you have imaginary positive, make it negative, negative make it positive. So 1 as it is, 1 as it is, I, now it becomes minus I becomes plus I. So this is a complex conjugate. Now you take the transpose. What is transpose? Row becomes column, column becomes row. Okay, so that I continue here. Well, I have already initially written our basic requirements, that is Ket 0, Ket 1, Bragg 0 and Bragg 1. Whenever required, I make use of them. Well, coming back to the Hermitian of this, Hermitian is nothing but transpose. So now I write straight away dagger, that is conjugate come transpose, that is 1 by root 2. Row becomes column, so column becomes row, 1 minus I becomes row, 1 minus I, and this becomes 1I, like this. Okay, so this column became row, this column became row. I hope you got it. Now you take the product of those two, U and U dagger. So U and then U dagger, that is equal to 1 by root 2. U is already here, 1 I minus I, into again 1 by root 2 I have to write. Anyway 1 by root 2 into 1 by root 2 is nothing but 1 by 2. I take off this root 2. Well, into U dagger, 1 by root 2 already clubbed with this, so I write 1 minus I, 1 plus I. Okay, please follow carefully. This is equal to, you can expect this for 5 marks or 4 marks numericals. That is equal to 1 by 2 into, well, you know how to multiply row into column, how to multiply the matrix, row into column, 1 into 1, 1. Well, 1 plus 1 into 1 plus 1. So 1 into 1 plus 1 into 1. Next, 1 into minus I. Well, 1 into plus I. Okay. Well, next, I into 1, I. Next, minus I into 1, minus I. Are you following? Okay, next, I into minus I square, I into minus I square. Next, minus I into I, again minus I square. Please follow carefully. That is equal to 1 by 2. Well, 1 plus 1, 2, plus I minus I cancel, plus I minus I cancel, minus I square, I hope you know it is nothing but plus 1, because I square is minus 1, minus into minus plus, again minus I square is plus 1, so that is 1 plus 1, 2, correct? And now you take 2 inside, 2 by 2 cancel and 2 by 2 cancel. Ultimately I left with 1 0 0 1. Yes, what this is? This is nothing but identity matrix. Therefore U dagger finally leads to identity matrix. Therefore U given in this form is definitely Hermitian, definitely a unitary matrix, So these types of numericals I will do it at the end just for the sake of continuity. I mentioned one numerical problem here. Okay, I give you one more assignment. You can try this. Just check whether U is equal to 1 by root 2 into 1 minus 1, whether this is going to be unitary matrix or not. Please check. How to check? First you find out complex conjugate, then you take transpose. What I mean to say, you find out U dagger of this, multiply U and U dagger. Definitely if it gives, by chance if it gives I, that means 1 0 0 1, then you can say this is a unitary matrix, otherwise this is not a unitary matrix. Okay. So this is about calculation of unitary matrix. Now let us move on to next concept, that is inner product. What is inner product? Before I take up inner product, let me explain something about dot product, which you studied in first PUC or second PUC or in scalars and vectors chapter in any other subjects. Even in physics also, like work done is nothing but dot product of force and displacement. Okay, you might have heard of this one, F dot ds. Electric flux is the dot product, E dot ds, dot product of electric field and surface area, ee tara. So dot product ಬಗ್ಗೆ ನಿಮಗೆ ಸ್ವಲ್ಪ ನಾಲೆಡ್ಜ್ ಇದೆ, ಅದನ್ನು ಸ್ವಲ್ಪ ರಿವೈಸ್ ಮಾಡ್ತೀನಿ. ಲೆಟ್ ಮಿ ಕನ್ಸಿಡರ್ ಟೂ ವೆಕ್ಟರ್ಸ್. ಸೇ ವೆಕ್ಟರ್ u is equal to x1 i cap plus y1 j cap. Next I take v vector v, that is x2 i cap plus y2 j cap. Now you find the dot product, not cross product, dot product of these two, then u dot v is equal to x1 x2 plus y1 y2. Understood? So you all know x1 y1 x2 y2, they are just numbers like 2i plus 3j, 4i plus 4j, something like that. So even x1 x2 also is going to be a number, y1 y2 is also a number. So number plus number is again a number. So what I mean to say, dot product or scalar product is going to give you, dot product or scalar product is going to give you a number, means a scalar quantity. Okay, so this is well known fact which we already familiar. We have done so many numericals at primary, basic level like PU or even in high school also in some 10+2 CBSE syllabus they might have done this. Anyway, back to this. This one in the vector form I have written. In matrix form how to write? In matrix form how to write I will tell you. See, U consists of elements x1 y1, V consists of elements x2 y2. Okay, now I have to multiply these two. How to multiply? I go for u into v like this. But if I write x1 y1 and then x2 y2, and if I keep on multiplying this, I won't get in this form, I won't get a number something like this. Actually I should get x1 x2 plus y1 y2, but if I write this way I won't get it at all. So what to do for that? Better you write x1 y1 in this form. That means column should be converted into row. That means u is now transposed, means you take u transpose, right? And then you multiply with v. So now let us check u transpose and v whether I get this form or not. X1 x2 plus it is not x1 x2, just x1 comma x1 y1, that is u transpose into v is x2 y2, correct? No, see, actually I wanted to try in this manner, but if I try like this I won't get the same result. My intention is to show you the dot product in matrix form also. This is in the normal notation form, normal representation form, vector form. This is in the matrix form, because in this chapter we make use of matrices, that's why. Okay, well, coming back to this, now multiply x1 x2 plus y1 y2. See, this is what I wanted, this is what I wanted, I got it. That means u transpose, this is not dagger, this is transpose, u transpose v is going to give you the same result what you get from the dot product. This dot product, if you write in this form, is going to be called as a inner product. Okay, so inner product is nothing but dot product only. If vector space is real, inner product is going to give you a number, give you a number. Suppose if the vector space is having complex numbers, definitely you are going to get a complex number. I will come to that little later. Before that, back to this. Well, you have inner product of two vectors. To find inner product, what we have to do, one of the vector transpose we have to write and then multiply, you get the inner product. Suppose if I take the inner product of same vector, same u and u inner product, if I do inner product of u and u, if I do, what I will get, that means dot product of same u dot u means x1 y1 y1, that is going to be x1 square plus y1 square, right? That is u square is going to be x1 square plus y1 square. I want just u, that is going to be root of x1 square plus y1 square. Dear students, this is very important point. Remember, this we call as magnitude, or we call it as length of the vector. This is nothing but here onwards will be called as norm. So when do we get norm? When the inner product of same vector, inner product is operated on the same vector, we are going to get norm. So square root of inner product, that means square root of mod u square is nothing but norm. Got it? Well, I repeat once again, inner product is nothing but dot product of two vectors. In the normal course, it is written in this form and with which we all are familiar. In vector space or in matrix form, we cannot write this way, because if you write, you won't get back x1 x2 plus y1 y2. So therefore, what I am doing, I change one of the matrix, one of the vector from column to row. That means I take the transpose. After taking the transpose, I multiply. When I do so, I get back the same result. I get back the same result what I get from the normal operation. So this is inner product. Inner product is obtained by multiplying the transpose of one vector with another vector. Well, if the inner product of same vector is taken, we are going to get the magnitude of that vector, length of that vector. In this particular context, we call it as a norm. Okay, well, this we are going to apply for that 0 ket or 1 ket or BRAC 1 or 0 1. How this inner product is applied here and what is the use of the inner product in this particular context, I will explain now. Okay, we shall proceed further. Now coming to inner product of Dirac notations or ket vectors or BRAC vectors in this particular context. As I told earlier, inner product in a real vector space gives you real number, whereas we are talking about complex vector space, so inner product of two members of the complex vector space definitely going to give you a complex number. So definition, complex vector space inner product. What is the definition? Inner product of two members of complex vector space is a product of those two vectors which finally gives you a complex number. So I have given the definition here, please follow that. Well, let us proceed further. I already told you what is the procedure to find the inner product. If I have a vector u, right, first I should find the transpose of that. But remember, in this particular context, it is not just transpose, it should be Hermitian, because here we are going to have even complex numbers also. So therefore Hermitian is more better than just transpose. So I have a vector u, find out its a Hermitian, and whenever you find the Hermitian, it is going to be the BRAC of that ket vector. Suppose if there is a ket vector like this, right, it's a Hermitian, means complex conjugate and then transpose is going to be, well, it's a ket, BRAC. So that means it is going to be like this. Suppose if I take the complex conjugate of this and then transpose, then I generate this particular state, means ket converts into BRAC. Okay, let me have two different vectors, not u alone. I have two different states u and v. I want to find the inner product of these two. Then what to do? I retain v as it is. I retain v as it is. Okay. Then I find the Hermitian of u, then this is ket v and this is ket u, sorry, BRAC u, then these two together is known as inner product. This is the inner product. Okay, so let me take one example and explain. Let v is equal to x2 y2, right, and u is equal to x1 y1. Then first I must find the what is called Hermitian of this. Hermitian of this is nothing but, or okay, in this case there is no question of complex conjugate, so I straight away go for BRAC. BRAC, how do you find? Just to transpose it up, that is nothing but x1 y1. Got it? Now you multiply these two, that of course this is ket v, this is now BRAC. Earlier this was also ket, now it has become BRAC. So BRAC u into ket v is equal to x1 y1 into x2 y2. So finally what will happen? x1 x2 plus y1 y2. By chance if any of them, either y1 or y2, x1 or x2, if they are complex, definitely in the final answer you will be having complex number, definitely. Okay, so this is the inner product. So inner product, how do you find? Two vectors or two states inner product, how do you find? Retain one state as it is, like v as it is. Another one you take the Hermitian. If there are no real complex numbers, just it is only transpose. That means you convert that ket into BRAC. Convert ket into BRAC and then multiply, you will get the number. Let us take one example. Let me have one particular example. Well, there is a ket u like this. There is a ket u. It is 3 plus I, first member, 4 minus I, second member. There is ket v. It is also having two members, two dimension, 3i and 4. Now the question is, find the inner product of these two. So u v question mark. So if I write like this, definitely it is going to be inner product. Well, what to do? Well, I have to first of all find out the Hermitian of u. That means BRAC u. How to find? 3 plus I must become 3 minus I. Okay, and then 4 plus I become 4 minus I, and now itself I convert rows into column or column into row. So this is column, I convert into row. It is going to become 4 plus I. I hope you got this. Please check once again. 3 plus I wrote it as 3 minus I and the complex conjugate and 4 minus I should write 4 plus I here, but I transpose it, so 4 plus I am writing here, and not only complex conjugate, I am also writing the transpose. So complex conjugate plus transpose is going to be Hermitian. So that is BRAC u. So now it is in this form. Now find out BRAC u into ket v. That is u v inner product. It is 3 minus I, 4 plus I. It is my BRAC, and ket no change, as it is 3i and 4 as it is, you have to retain. That is equal to, solve it, this into this. Okay, I write it one more step. 3i into 3 minus I plus, right, so you need not have to put this 5, because finally I am going to get only one number, that's all, plus 4 into 4 plus I, right now. So like this is step x1 x2 plus y1 y2. Similarly x1 x2 plus y1 y2, that's all. That is equal to 3 3s are 9i minus 3i square plus 4 4s are 16 plus 4i, right? That is equal to 9 plus 4 13i plus this is 3. You know why it is 3? Yes sir, because I square is minus 1, minus into minus plus, that is 16. So finally I will have 19 plus 13i. Dear students, please check this equation. What did I told? Inner product of two members of the complex vector space. Nodi ivu complex vector space in a numbers. Henge heltira sir? Because there is a complex number. Anta ಎರಡು ನಂಬರ್ಸ್ ಗಳ ಇನ್ನರ್ ಪ್ರಾಡಕ್ಟ್ ಅನ್ನು ತಗೊಂಡ್ರೆ ಫೈನಲ್ ಆಗಿ ನಾನು ಏನು ಬರುತ್ತೆ ಅಂತ ಹೇಳಿದ್ದೆ? ಕಾಂಪ್ಲೆಕ್ಸ್ ನಂಬರ್ ಬರುತ್ತೆ ಅಂತ ಹೇಳಿದ್ದೆ. ಬಂದಿದೆ ನೋಡಿ, 19 plus 13i. What did I told? If you take the inner product of two members of a vector complex vector space, definitely you are going to get a complex number only. Here x2 x1, sorry, this is actually x2, this is not x1, sorry, x1, it is not x2, x1 x2, x1 x2 is 19, y1 y2 may be 13i, or even other way also, either first number may be complex or second member may be complex, but in total it must be a complex number. Well dear students, let me take one more simple example, then I proceed further. Okay, so let us find the inner product of ket A with itself, AIB, right? This is the member of one vector family, vector space family, complex vector space. Now there are no two vectors, only one vector, its own inner product you have to find. What I mean to say, find the inner product A itself, that is question mark. Remember, in the just a few minutes back I mentioned, when you take u like this, you are going to get what is called magnitude, right? Let us check whether we are going to get magnitude or still we get only imaginary, that means complex number. So here you can see the difference and you can understand the real meaning of inner product, what it is. Let me proceed further. So straight away I will write bracket A. So A as it is, IB becomes minus IB. Dear students, please follow carefully. I have written not only complex conjugate, I also do transposed. This is Hermitian into ket A, that is AIB. Okay na? That is this into A, well A, that is x1 x2, that is x1 x2 or x2 x1, that is A into A minus IB plus IB into A minus IB, that is equal to A into A square minus I into AB plus again I into AB minus I square B square, I square, B square. Okay, minus I plus I cancel. This will be A square plus Y plus, yes sir, because it is I square. Minus I square is plus B square. Look at this. When I take inner product of the same vector, I am going to get the magnitude. So no complex number here. This is what I mentioned. So same vector inner product always gives you magnitude. Okay, well, after explaining so much about inner product, coming back to our present particular situation. In our present case we have zeros and ones. Okay, now let us take the zeros and ones and do the inner product of them. Inner product kade onchur lod. Let us take a look at the inner product of these numbers. Okay, first I take inner product of 0 and 1. Whether you write 1 0 or 0 1, that is a question. Well, I take 0 into 1. Okay, well, just 1 minute. I find inner product of 1 and 0 state. 1 and 0 state. Well, by now you already know how to find the inner product. Look at 0, 0 remains as it is as 1 0, but ket 1 now it should change. You have to go for transpose. There is no complex conjugate of ket 1 because there is no complex number. So straight away you can write this as, see 1 is 0 1 alwa. So you write that as 0 1 in the row form, and ket 0 is 1 0 0 alwa, 1 and 0. Okay, find out. That is equal to 0 into 1 0 plus 1 into 0 0, so that is 0. That means inner product of 2 qubits in 0 ket state and 1 ket state going to give you 0. Final answer is 0. Let us check the other one. Other one means this is first possibility. Second possibility, that is the inner product of 0 and 1. First one I did inner product of 1 and 0. Now I am going for 0 and 1 inner product. Yenagutte? Let us see. Okay, this is equal to brack 0. Just change this to row. No question of conjugate because there is no complex number. Well, 1 0 into 0 1 ಮಾಡಿ ನೋಡೋಣ ಏನಾಗುತ್ತೆ. 1 into 0 0, 0 plus 1 0, it is going to give you 0. So whether you take the inner product of 0 and 1 or 1 and 0, that is going to give you finally answer as 0. Dear students, I ask you one simple question. I told you inner product is nothing but dot product. If dot product of two vectors is going to be 0, what might be the angle between them? Can you guess? Can you recall from your memory? PUC ನಲ್ಲಿ ಓದಿರ್ತೀರಾ ನೋಡಿ, ಎರಡು ವೆಕ್ಟರ್ಗಳ ಡಾಟ್ ಪ್ರಾಡಕ್ಟ್ ಯಾವಾಗ 0 ಆಗಿರುತ್ತೆ? Only when the angle between them is 90 degree, because the dot product is nothing but A dot B PUC. A dot B is equal to AB cos theta. When this is going to be 0? Only when theta is equal to 90 degree. So if two vectors are perpendicular to each other like this, when two vectors are perpendicular like this, their dot product is 0. Similarly here, inner product is nothing but dot product only. Inner product in case of vector space, normal course it is called as dot product. So inner product of two vectors in a complex vector space is 0, means they are perpendicular to each other. Well, perpendicular to each other means what do you mean by perpendicular to each other? Normal to each other. ಇನ್ನೂ ಒಂದು ಹೆಸರಿದೆ, ಏನು ಹೇಳಿ ನೋಡೋಣ? ಆರ್ಥೋಗನಲ್. Okay, so this is called as orthogonality. What is the condition for orthogonality? If the inner product of two vectors is 0, then those two vectors are said to be orthogonal. Got it? So now I can say ket 0 and ket 1 are perpendicular to each other, orthogonal to each other. I hope you are following now. Well, I explained the orthogonality, how to find the inner product of our qubit 0 state and 1 state. So here I operated 1 on 0, 0 on 1. Let me take the inner product of same like this. A on itself, 0 on itself, 1 on itself. Let us try what will happen. If I take the inner product of 0 on itself, that means 0 0 like this, what will be the answer? Let us try. You know 0 0, well 0 is 1 comma 0. I have to write it as 1 and 0 in this form. Okay, so 0th state, brack 0 1 0 I have to write into ket 0. Ket 0 in the column form itself. I hope by now you know how to find the inner product. ಎರಡು ವೆಕ್ಟರ್ಗಳ ಇನ್ನರ್ ಪ್ರಾಡಕ್ಟ್ ಅನ್ನು ಹೆಂಗೆ ಕಂಡುಹಿಡಿಯೋದು? ಒಂದು ವೆಕ್ಟರ್ನ ಹಾಗೆ ರಿಟೈನ್ ಮಾಡ್ಕೋಬೇಕು, retain as it is. Another vector you take the Hermitian, and you know how to find the Hermitian transpose of complex conjugate. If there is no complex number, just you take the transpose. That's what I have done here. Well, do it. 1 into 1 1 plus 0 into 0 0 is going to be 1. So inner product of the number 0 on itself is going to give you 1. Let me try another one, 1 1 state. That means this becomes 0 1. Okay, 1 I should write in the brack form, and another one I should write in the ket form is going to be 0 0 0 plus 1 into 1 1, so it's going to be 1. Dear students, observe one thing here. When the inner product of the same vector is taken, it generates the value 1. Okay, either this or this. If any vector satisfies this property, then we call it as normalized vector, normalization. After all, what is normalization? Normalization is nothing nothing but modulus of alpha square plus modulus of beta square equals 1. If beta is 0, alpha square is 1. If alpha is 0, beta square is 1. That is maximum value is 1 normalization. So 0 ket is a normalized vector. Ket 1 is also. So this is normality. Now I club these two. So in this part I explained it orthogonality. In this part I explained a normalization. Clubbed both. Then I call 0 and 1 as not only orthogonal, not only normal. I call them as orthonormal. Orthonormality. Orthogonal plus normal. That is the thing but orthonormal. So ortho means vectors are perpendicular. Normal means their magnitude finally going to be 1. Okay, so this is nothing but norm. I told you no, norm. So inner product of u under square root is going to give you the magnitude, that is nothing but normalized value, that is nothing but norm. Okay dear students, so far I explained you what is inner product, how to find the inner product, how it is applicable to our 0 and 1. See, whatever mathematics may be, finally we have to come down to that 0th and 1 state. Remember, we are talking about quantum computation, and for us that ket 0 and ket 1 are very precious, very important terminologies, and we cannot get away from them at all. Whatever you discuss, ultimately you have to come down to that 0 and 1. That's what I am doing even now also. Nodi, I started with inner product, finally I came down to ket 1 and ket 0 and ket 1. So brach 0 and brach 1. So I am telling you these qubits what I have selected, that is ket 0 state or ket 1 state, are perpendicular to each other, means orthogonal to each other, and normalized also. So they are therefore called orthonormal, okay, vectors or orthonormal states. Well, I stop here. I come back to you with the next topic, that is Pauli's matrix. Okay, thank you.